All right, let's get back to something I talked a little bit about already. Something a bit less abstract. The idea of continuity. So we're in section 2.5. So let me see if you guys. Yeah. All right. Make sure. Good. I can do that. Sweet. Yeah. Let me ask you a couple questions. Does the limit as x goes to a, f of x, does it exist? Yes. Why? Because they agree. The limits from both sides agree. So you can just write a consolidated statement. You don't have to do it side specific. Does f of a have a value? No. I like it. Would you say that this is continuous through a? We talked about continuity once before. So like, can I drive down this road from here to there? Can I get there from driving down this road without leaving the road or something, or jumping around? This is a big old freaking sinkhole in the middle of the road here, right? I get right here, and my friend, we both agree where the sinkhole is, don't we? But we can't get to each other. So it's not continuous. I can't draw that without lifting up my marker. That's the most basic way to define continuity. Let's get a lot more specific with what continuity is. What could I do to this if I'm the math god and I could change something? What would I do to make it continuous? Or physically, yeah. Physically, if it's a freaking sinkhole, how do we make it passable again? We fill in the freaking hole. So what am I doing if I do this, though? What am I doing? What did I just do? Yeah, I made this one, not false anymore. It does have a value. So now, not only does the limit agree from both sides, not only does it look like the function is going to a certain value from both sides, but the function actually gets there. It actually equals that value, right? How do I capture that in math? Not only does the limit exist from both sides. Is that cool? If I don't put a plus or minus, it's inherently both sides. Not only does this exist, yeah, but it equals f of a, which is a weird situation for a limit sometimes, right? A limit, I don't really give a shit what it is there, but most often in our questions, it isn't equal to that function. The function is just an open circle there or something. If that circle is filled in, then it's continuous. If I fill in that sinkhole physically, a bunch of gravel or a bunch of crazy people, then I can drive across, right? Okay, maybe. That's almost too simple to believe. So this is merging these two ideas. The limit doesn't give a shit about what happens there. But if the function value there is the limit there, it's continuous. You can actually just go straight through there. I don't have to stop to make a little open circle. I just keep going. Yeah. So like right here, is it continuous at that point? Well, yeah, right? So everybody always kind of forgets that. There's a whole bunch of freaking points. I focus on this first because there's no circle there. But now this function is continuous. Let's say this, it starts here and ends there. It's continuous everywhere on its domain. Right? So there's a lot of functions that are continuous everywhere on their domain. How about sine x? Is that continuous everywhere? Totally. Here's one that'll trip you up. Because I don't know if you guys are listening to how I'm saying this. What about tangent x? Is it continuous on its domain? I love you guys. On its domain. So what's the domain of tangent? Where does tangent have a problem? Let's see, what's on the bottom of tangent? What's tangent? What over what? Sine over cosine. So tangent's going to have a problem when cosine is 0. When is cosine 0? Not want to say.
2x and 0? Is that what you're asking?
When is cosine pi over 2? Cosine is 0 at pi over 2, 3 pi over 2, negative pi over 2, all the pi over 2's, right? So when is tangent going to have a problem? It's going to have a problem at, for example, negative pi over 2, pi over 2. And that's why there are vertical asymptotes. So are those in the domain of tangent? What did we just say? Are those in the domain of tangent? No. Is tangent continuous everywhere on its domain? Which means don't give a shit about these values because they're not in the domain. It's continuous everywhere else. Yeah, it's a beautiful little cubic looking function, right? It's kind of freaky. Think about it. Yes?
So that's considered continuous?
On its domain.
Okay, so it would be specific instead of just saying like
Yeah, so there's a theorem coming up that's very specific. It says all the trig functions are continuous on their domain. All radical functions are continuous on their domain. All these different functions are continuous on their domains. That's what that tells you. Is that cool?
Yeah.
I like it. I like it. Now, if I said, is tangent continuous at pi over 2? Oh, hell no. It's so not continuous at pi over 2. Is tangent continuous on its domain? Yes. I like it. Maybe. Okay. So let me break this down a little bit. So this is good enough to capture all the ideas. But let me lay out all the ideas that has in it. This has a ton of ideas in it. First idea is that the limit as x goes to a from above equals the limit as x goes to a from below, or from the right, from the left. Secondly, it says that the limit as x goes to a of f of x is this. Right? I mean, it's what it says straight up. And there's some third thing. It's really silly. I don't like to break it up because it's all right there. Right? So the limit exists and it equals the function value there. But when I write this does say the limit exists already. It already says it exists from both sides and agrees. That's what this symbol means. But in the book, you'll see they break it up a bit. Where'd you go? No, it's not there. Oh, right here. Here it is. F of A is defined. Okay, that's the thing I forgot. The limit exists, and the limit. So you really just need the third thing. This says that F of A is defined. It says that the limit exists. It says it all in there already, and that's really the absolute definition. Is this? That's the definition. I like it. So, for example, here's a function that's continuous on its domain. Let me ask you how we're fair about it. So like the square root function. What's the domain of this? Yeah, 0 to infinity. So, and of course it looks like this. So, is it continuous here? That is a really freaky question. Everywhere else is fine. Why is it continuous here? Because the limit exists and it equals the function value there. I love it, right? What's freaky about that point right there? Can it come from both sides? No. So to be fair, if it's an endpoint, we don't force it to come from both sides. We force it to come from the side that it exists on. So this is continuous here because the limit as x goes to 0 from the right, is 0, which is the square root of 0. The limit is 0, which is the function value at 0. You guys with me? So to be fair, we got to be fair to these poor little functions. It's got no chance. It doesn't exist back here. So you can be continuous at the endpoints from just one direction, to be fair. So is this continuous on its domain? Totally.
So it's minimum one direction. It doesn't have to be two directions, or is it different?
Yeah, it does, well, the only time we don't consider two directions is if it's at an endpoint where the domain kind of ends. Yeah, I like it. I like it. Let's see. Blah, blah, blah. Blah, blah, blah. And then it gets into, okay, let me jump to the chase here, because obviously, what's true about polynomial functions? They are just the nicest freaking functions that ever existed. They're continuous everywhere. Rational functions are just ratios of polynomials. They're continuous on their domain. On its domain. You'll see this phrase a lot. It's any rational function. So, if you remember from pre-calculus, oh, I've done it to myself now. I hide that thing from you. There it is. High-tech eraser that we have. So, what do you remember? Remember these rational functions? You had to find the vertical asymptotes, the horizontal asymptotes, and then they lived in these little regions. So maybe it looks like this. Yeehaw! Woohoo! Yeehaw! And you got over the fact that the horizontal was a suggestion; it wasn't a wall. You can cross the horizontal how many times? Infinite number of times. These are freaking walls, right? It's a trap. Pull up. But you can see this problem spots are the horizontal the vertical asymptotes, but in these regions they had to be continuous. Because you identified the problem spots, so there can't be any problem spots otherwise. I like it, I like it, I like it. Sweet. So they're continuous on the domain. Okay, blah, blah, blah. So, here is that one theorem I was talking about. So there's everybody. Polynomials, rationals, roots, trig functions, inverse trig functions, exponential functions, logarithmic functions. They're all continuous on the domain, all of those suckers. So any combination of those, if I add a trig function to an exponential function, and then subtract a rational function, that's all continuous on its domain. So that's how that kind of inherits that continuity. I think I already used these words with you guys about problem spots. Let me give a little better picture here. Let's see. Right, that's good enough. And then we got boom and boom. Okay, so there's some discontinuities. So what kind of discontinuity is an A? I don't know if you guys remember. I'm not really sure if I used the word yet. There's a problem at A, right? Can I remove the problem? Remember what we did earlier? I could remove the problem if I defined f of A to be this, whatever that is. Is that cool? Like we did earlier. Fill in the pothole. So this is called a removable discontinuity. I'll even write the whole word out. So he's going to freak out later. Removable discontinuity. So is this removable, this one? This is the one I know I said the word for this. Jump. Yeah, that makes sense. What's the function do? It jumps. So this is a jump discontinuity. And what do you think I'd call this one? It goes to infinite discontinuity. So this is an infinite discontinuity. Blah, 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 blah. I like it. So, on the reverse of that epsilon delta proof sheet, there's problems dealing with continuity. Hopefully, my printer did correctly. Yay! So if you turn that sucker over, you see this. So give that a try. Give that sheet a try. You can call me over if you need some help. You can work with somebody near you.